Hi, everyone. Welcome to David Park's Tech Talk about UAVs in New Zealand. I met David when I was down in New Zealand doing a little trip for Google, and the government introduced people to you service folks said, what are you interested in? I said, well, one of the side projects that I sometimes help with, very minorly I should point out, is some of our imaging efforts. And they said, oh, well, you have to talk to David Park. And I'm like, well, okay. So we met via video conference, and I said, boy, you know, this guy's really a kindred spirit with some of the folks here in Mountain View. And so I invited him to come and speak, and he graciously accepted. So I don't want to spend too much time. It will be recorded for Google Video, and will be exposed externally, so keep that in mind. We will have Q&A at the end, at which point we will stop recording so you can ask your real questions. So there you go. David?
Thanks very much, Chris. I do apologise, I'm a proper academic at heart, so I've got about 60 slides here. I'm going to charge through them at a rate of knots, and hopefully we'll have some time left at the end for questions and answers. If anybody gets too bored, just throw something or doze off or some such, and I'll know to move on. So what I've actually got here is an introduction to my research centre, the Geospatial Research Centre. Within that are a range of things, and so we've got a bit of background and then the fun stuff, a quick technical overview of the research areas that we cover, some of the skills we've got, some of the experiences we've got related to imaging, UAVs, sensor integration, that sort of thing. One slide about the future, and then hopefully, as we've heard, a chance to talk and engage in discussion. So without further ado, let's charge through these. A bit about my background, just to put it in context. So I did my 3 degrees at the University of Nottingham, civil engineering, built motorways for a while. It was quite hard work and in the outdoors. Got a master's in artificial intelligence and robotics, and then my PhD was in airborne digital photogrammetry. Went out to the real world for a while at the University of Nottingham, spin-out company, basically developing contracts and managing contracts from the European Space Agency, European Commission. Did that for a few years, went back to the Nottingham as a senior research fellow, responsible for generating cash and initiating new research ideas, which included underwater positioning, unmanned aerial vehicles, and a range of other fun stuff. As all that was going on, I reached the ripe old age of 30 and thought, wait a minute, there's more to life than this, being just a senior research fellow in a world-leading university. I want to have a go myself. And so in March 2005, and it did take slightly longer than the time it takes to say this, I had an idea about setting up a new research centre. So far, so normal. I actually wanted it to be world-leading, fine, but I'd enjoyed the flexibility that I'd had in industry and being a company. I wanted to have a research centre that was academically excellent, but commercially aware. And I was looking around for somewhere where there was no incumbent. So I identified New Zealand as somewhere that didn't have the sort of things we were talking about. So rang up the New Zealand Embassy in London, said, I've got a good idea, can I have $3 million, please? And they said, well, can we meet you? Well, fair enough. And so I said, well, look, we're going to provide you with this world-leading centre, and these are the sort of technical areas that it's going to be really excellent in. And they said, that's great. For 18 months, they did actually listen to me and then fly me down to New Zealand for a quick trip. We had various visits, discussions with potential partners, all sorts of feasibility studies, lots of phone calls in the middle of the night. Depending on what time of year it is, it's either 11, 12 or 13 hours time difference between New Zealand and the UK. I'm a big fan of Skype now. But by October last year, we'd finalised a number of things. So Christchurch was confirmed as the preferred location. We'd actually chosen to set up a limited company to be the vehicle for a joint venture between the University of Nottingham, the University of Canterbury, and the Regional Development Agency. There we are. It must mean it's getting dull already, I guess. We'd secured my $3 million from the government and the region, and 7 or 8 underpinning documents were finalised and agreed, and that was a bit of a feast for lawyers, I'm afraid. Joint ventures, IPs, shareholders agreements, service level agreements, etc. We commenced operations 13th of November last year. It's not just me. I brought some of my colleagues from Nottingham down with me as well. The guy on our left is our pilot. The rest of us all came down from Nottingham. Every small startup needs a pilot, I fear. And this was at our launch event, which was held in April, just gone. And we've got a good team, good experience, all reasonably young, reasonably enthusiastic with a range of skills. And again, if we have a chance later, we'll go into some of the details. But you'll see as we go through the presentation, the various skills that these guys are bringing to the party. Just in case none of you have had a chance to visit New Zealand, I thought I'd better put up a map showing you where we are in the world. So on the left-hand side there, we're that little island. That isn't actually a real red ring around us to keep folk out. That's just where we are. Next to Australia, down to Antarctica, down the bottom there. and I made the short hop on the plane yesterday over the Pacific, which is why I'm slightly dopey at the front here, I fear. Christchurch, on the right-hand side there, you can see is down on the right-hand side down in South Island. So 2 main islands in New Zealand, and we're down sort of middle right on South Island. Again, if none of you have had a chance to visit the beautiful garden city, then the population is about 300,000, which is a third of all the people on South Island, which is about the size of England, so it gets pretty crowded. You can see that up on the left there, that it's just above a couple of extinct volcanoes, which make nice hills for gliding off, apparently, and just some touristy shots showing the mountains in the background and how barren the whole place is. That's actually all of Christchurch. That's not just downtown there. That's actually the whole lot. So this is what we do very well. There is more to it than that. 4 things. The rest of it's just flaffle around the side. 4 things that we actually do really well. The first is positioning. So GPS, ultra-wideband, SUD-lights, which are ground-based GPS light transmitters, laser systems, LORAN, you name it. We understand the systems, the antenna, the electronics of the receivers. Interesting. I'll just carry on until someone shouts, it's fixed. So we actually do positioning in its widest sense, thank you. And that's from processing, understanding the systems, etc. Related to that is orientation. So accelerometers, gyroscopes, inertial sensors, dead reckoning systems, magnetometers, camera systems, multiple antenna GPS systems, you name it, various different ways depending on price or budget or performance or weight limitations, etc., to actually give you an orientation solution. As well as my background in photogrammetry, one of my colleagues is an expert in computer vision, machine vision, image analysis. So we've got an imaging strand as well, which is not designing sensors, but it's actually getting data from them, calibrating sensors, getting useful stuff out of those systems and sensors in the real world. The fun stuff, and by far the hardest bit, is actually optimally integrating some, none, or all of those together in the real world against some sort of application or need, either internally driven or externally driven. That's it. That is our core business. That's what we're really good at. The application of those, and this is just what we're playing in at the moment, is reasonably limitless. I've not yet found a meeting or an organization or a department or a group where we haven't got some sort of link across. And there's just a flavor of some of the things we're playing in there. Across a range of across a range of platforms, sorry. So we've been going for 5 months. We've got 5 staff employed. I've got a ridiculously overpowered board of 7 people, including the former governor of the Bank of New Zealand, and et cetera, et cetera. They all seem quite keen to support what we're doing. We've got 2 PhD students already in post, jointly supervised with mechanical and mathematics departments at Canterbury. I've got 8 more great CVs sitting on my desk at the moment. We've not advertised at all. These are folk who've just already proactively approached us from the US, from South Africa, from UK, from within New Zealand, saying, look, we've heard what you're up to. We want to come and be part of it. Here's my CV, please. We've secured 8 commercial contracts already worth about $300,000. And you can see the organisations down here. A couple of UK companies, the rest are New Zealand-based, Trimble just down the road in Sunnyvale. And so it's a reasonable mix already of contract work. So not bad for 5 months in. The long-term vision, as you would expect, I imagine, in-house and collaborative R&D at the PhD and postdoc level. I don't want to teach masters or undergraduate students. We've got big locks on the doors to keep those great unwashed out of our lovely research centre. We will develop great IP and hopefully make our millions commercialising it, maybe. We will be a world-class centre for geospatial research, training, education, and grow sustainably. It's only going to happen with, as we know, the strategic and effective links with companies and academia, both in New Zealand and, more importantly, overseas. I'm now going to charge through 5 what I've called internal research themes and activities. And again, this is where we drill down to some of the sort of technical activities that we've done in the past or are doing now. And I've also put a quick few slides up of some of our plans for the future as well. Obviously, with the commercial contracts we've got, within reason, we do what the client wants, and we deliver it, and we do it very well. It is all related to our core business. We don't go around building wardrobes for folk or anything too untoward. But internally, while we're still ramping up the workload, we're actually developing a number of things internally that are related to our core business, and so this is what I'm trying to give you a flavour of now. First of these is positioning and orientation. So we do have the proven ability to integrate at both hardware and software levels a wide range of navigational position sensors. There's a list up there. We've never done all of them at the same time. I can't quite see a situation where we might, but individually or in smaller combinations, we've played at some level with every sensor that you see up there. And at lesser or greater extent understand the systems, the error models, etc. So we've got a reasonable experience there. One of the key bits of IP that we have is our internal integration software called Point, which is an incredibly flexible interface for integrating sensors. So internally, for the first 3 months while we were still getting warmed up, this was the focal point of all of the effort of my team while we weren't doing external work or charging around trying to get contracts, was actually putting Point into some sort of reasonable form where it's got documentation, it's all in the same language, it's got robust interfaces that are well understood and documented. And so we can actually just define different measurement types, position type, velocity type, attitude, etc. And then that allows us to integrate systems very quickly. For example, GPS INS or GPS and barometer and odometer, you name it, those can all be defined as a position type. If not, we can define a new one and integrate it into the system. It provides our core GPS and GPS INS processing engine of all types. So cheap and cheerful up to very expensive. It can process Galileo data, which doesn't exist yet, which is Europe's GPS system, modernized GPS, you name it, we can do it in there. And that's all internal and all under our own IP, which is quite a nice thing to have. The integration itself is fairly flexible, so a number of Kalman filters running in parallel. We can just keep adding more to the bottom, as long as we can define a class. It could be a pressure, it could be a range, could be an acceleration, whatever it might be. As long as we can understand the sensor and model it, we can integrate it and get some sort of optimal solution for position, orientation, velocity, etc., out of the end. It could be real time eventually. At the moment, it's just post-processed. I've just put a few examples here of work that we did just as we were leaving the UK, just to prove a point of it's not just nice software, it's actually out there working with real data in the real world and getting data that, I will be careful what we say, is at least as good as that available from commercial systems. So this was some work we did in marine trials with 3 different grades of inertial unit, which we had at Nottingham. Navigation grades out of the nose cone of a cruise missile. Low cost, we mean a few $1,000s, MEMS sort of sensors. And after a 30-second GPS outage, so just on the inertial alone, these are the sort of position accuracies that we were getting horizontally and vertically running through our Point software. And that's better than what you can get from the truthing systems that we had with us. Here's some more data just to prove a point. So in an urban area, DGPS, I don't know if you can see the yellow dots there. That's the only places where we've actually got GPS coverage. The rest of it's using about $3,000 to $4,000 worth of hardware and trying to both in real time and then post-processed get the best position and orientation solution. So you can see on the right there, those of you who play with GPS know you need at least 4 satellites to get a fix. If we're operating in a standalone mode, we're hardly getting that at all. Most of the time it was just 2, sometimes 3. But as you can see from the blue dots, we were within about 5–10 meters in real time, and then post-processed, we were within better than a meter to the solution. And it wasn't just position, we were post-processed getting the heading error down to better than a degree. So this is real things in the real world with real data, with real problems, and that underpins a lot of what we're trying to do, is actually say, it's great to be sitting in an ivory tower and all academic, bugger all use to the rest of the world. Get out there, prove that something works in the real world, and get a solution that's as good as, if not better, than what already exists, if indeed one exists at all. So we've got a range of real-world experience, and these are just some slides, mostly of stuff that we did in the UK, but it's the team that I've got with me that did this work on a range of vehicles, in a range of environments. Top right, slightly comedy-looking piece of hardware. That's actually got 4 different types of inertial, ultra-wideband sensors, 2 different types of GPS, and all sorts of data loggers, which is why it looks ungainly, but was proving some trials for indoor-outdoor positioning research that we were doing. Again, I'm charging through these, and hopefully we'll get some discussion at the end. The internal plans that I'm happy to talk about for what we're going to be developing or looking to develop internally related to this area include low-cost GPS attitude estimation, so a couple of low-cost GPS antenna on wings of a UAV, for example. Doing centimetric positioning with low-cost, a few $100 type GPS receivers over short baselines, by which I mean 10–15 kilometers. Precise point positioning, so anywhere on the planet using dual frequency RTK solutions to get your position to centimeters without a base station. Actually evolving the point software to include more dead reckoning sensors particularly, but actually making it even faster to just plug and play sensors together based on some external requirement or need. And then looking at the ultra-tight GPS INS integration, which I'll come back to later, which is actually required to get into the software tracking loops of the receivers. You can't do that unless you're a receiver manufacturer, which we're not. So we've worked around that, and we have a development along the lines of software positioning receivers, which I'll show you next, which starts enabling us to do that sort of research. So signal analysis. One of the key things in this area for us is that apart from the satellites, GPS, the Chinese Beidou system, the Russian GLONASS system, there are other RF sources existing in the environment surrounding us as we speak that you could use for positioning. Cell phones, high-definition TV, ultra-wideband, Wi-Fi, Bluetooth, etc. So why can we not develop some sort of magic black box in software that integrates all the available signals dynamically in real time? Doesn't exist yet, but it's a nice vision. There are a number of, as I mentioned, benefits in terms of the processing if you can actually start getting down to that level. And so we're exploring what we need to do to make that vision a reality. On the right-hand side is the integration filter. That's our point software. We've got that already. Left-hand side, there's all sorts of sensors in the real world. Fine, they exist already and will continue to be developed. The digital acquisition front end we've now got, and we've proven that exists. So now we're working out how to get streams of bytes on a hard drive into some sort of form that the integration filter can make use of, which is not an unsubstantial task, but we're working on it, and we've already got it working for all of the satellite navigation systems that exist at the moment. So the hardware, just to show you that it's not just talk again, this is real kit that we've got. So a high-speed FPGA-based unit for actually grabbing any bits of the frequency from 0 hertz up to at least 2.4 gigahertz, as far as we've got at the moment. You can actually work with more than one source at the time. So we can be going out there, recording this information, and at the moment, grabbing it onto a hard drive for post-processing. You've then got to do something with it once it's there. So we've actually had to get the software working to actually make use of that data now you've grabbed it. So those who are into GPS, in the middle there, you can see a classic L1 acquisition there. And this is all using our software off data that we've extracted from the digital front end. There are a number of benefits. GPS receivers typically only record at 1, 2, or 4 bytes. We're recording at 16 bits, sorry. So there's a degree of benefit there in terms of the processing in what you can do. We can mitigate all sorts of problems like multipath based on that extra data. And you can actually integrate many different sensors at the same time. It's not there yet. It's not out in the real world. It's not a commercial product. But we're moving reasonably rapidly forward in this space. So in this area, then we need some prototyping tools that we're going to develop just so we can actually start being a bit more responsive in signal processing requirements. Non-GNSS signal activities, GPS fingerprint positioning. So in this room, for example, unlikely to be any direct GPS, but the multipath, particularly from terrestrial positioning and ranging signals, would be reasonably consistent. So we can actually position ourselves from the multipath and the error sources. And we've proven this with buildings in New Zealand in GPS. You can actually position that way rather than needing the direct signals themselves. If Galileo ever goes off the ground and gets itself sorted out, then there will be potential to rapidly prototype some of the commercial signals that will need to go against that based on the systems we've got. Image analysis and visualization. All right, charging through this. I don't need to tell you guys this, but images are a very rich source of data. Increasingly prevalent sources of information, a few dollars or less sensors, ubiquitous. We've got a picture of one of our videos, taking a picture of one of our UAVs on the worktop there. And what we actually need to do is do something useful with that information. Trying to tell us something about what's going on there, what's happening in that image. Easy to say, easy for us to do as humans, very tricky to program effectively, as many of you will be aware in the computer land. We have 3 areas of interest in the image analysis area. And this is quite a complicated slide, so I'll just go through the headings. The first is actually to take imagery and models of the real world and work out, i.e. navigate in the real world using that data. So I see something, or I have a series of images of somewhere. I can work out, based on my knowledge of that environment, where I am and where I'm pointing. You can actually combine knowledge of where you are and imagery to actually create models. So the classic example would be airborne photogrammetry, where we're flying along, we know where the sensor is, we're taking images of the ground, and we can reconstruct that afterwards to actually create 3D models of the environment that we flew over, for example. The fun stuff is actually where you may have heard of SLAM, simultaneous location mapping, where you're actually, from pure imagery alone, in theory, generating the models of the real world and some idea of where you are and where you're pointing. It will rely on, certainly in the short to medium term, input or integration with other sensors to actually aid you in that. That could be GPS, INS, etc. Those are the 3 broad areas. Underpinning it, some fun stuff, and again, it's all incremental steps with an end game in mind. So one of the important areas is to do motion tracking, preferably in real time. So this is a nice example of one of the PhD students of one of my colleagues, which was real-time tracking juggling balls. which sounds nice and easy, but it's actually quite complex if you've got identical juggling balls and looking to do it in real time with just a consumer level web camera. And so you work that one out, and that was fine, but distinguishing between objects, using knowledge of the real world and the physics of the real world to actually constrain your solution, dealing with occlusions, etc. There's another nice one that we've done, tracking ducks, which again sounds nice and easy, but actually has a pretty tricky problems associated with it. If you've cracked it and can understand how to do it, then there are potential benefits elsewhere. Again, feature matching. So a number of ways of doing this. This is some internal data that we actually captured from one of our UAVs. This is airborne data that we're of our own creation that we're playing around with this on. So again, it's relating it to the real world, doing it in the real world. We're looking for features that are invariant, ideally, to translation, rotation, and scale. And I've put within reason there. You can't take a picture of the top of this table and then something way over there from underneath it and hope for it to work. But within reason, we're certainly up to plus or minus 30 degrees on the rotation, for example, at the moment. You can then match those invariant features, hopefully, across one image or a number of images or a number of data sets based on that invariant description. But again, it's getting out there and doing that. It's not real time at the moment, it's near real time. Once you've got that, then we can start looking at stereo matching. So if we've got features, we've got the ability to compute epipolar geometry between images, for example. If you're given a point in the top image, the green line is the epipolar line, and the bottom image, an area-based matching, and this is real time, we'll actually then pick the most likely point for the match. So again, it's getting out there, it's doing it. Other folk may be doing this as well, but we're doing it as well from our own UAV data in this case. And all of these skills underpin that vision, as I alluded to a few slides back. So this is just another example, one of our little model aircraft UAVs. And again, the data at the bottom's captured from that UAV. So vision is a navigation sensor. We track points in the world, and then the knowledge of the movement of those points through frames actually gives us important information to either give us the position orientation from the aircraft or help constrain the solution that we might be having from the GPS INS. So I'll flip back and forwards between these two slides in a moment. But vision on its own is pretty good at determining many of the things that we may need to sort out for ourselves, and it is another source of information into the solution. So if you look at the pictures at the bottom there, so these are consecutive images, you can see it's tracking features, it's then working out where they've moved to. The opposite of those is effectively where the aircraft's actually moved. Sounds simple, but again, get out there and do it. Various simple sensors that we've got, a few web cameras, video cameras, digital SLR, various bits of software, both externally procured and internally developed for calibrating cameras, detecting features, matching in stereo. Bottom right, there is a nice instrument, Texas Instruments board that we're procuring at the moment, due for delivery this week, which we're quite excited to be playing with. It offers all sorts of potential. We're hoping to secure a thermal infrared sensor within the week or two as well, which again could open up all sorts of application areas for us. So just some pretty screenshots. So laser scanning, bottom left, that's Lincoln Cathedral. Top right, some of our UAV data going through Leica Photogrammetry Suite, which is a commercially available mapping software. Bottom right is a bit of software from Australia called Australis for calibrating cameras very quickly and rapidly. And it's generating these value-added products. It's putting it through the whole of that process chain and then exporting it in some format that's of use to somebody externally, whether it's CAD, video, a pretty picture, augmented reality, you name it. And that's up to, if you like, some sort of external client or requirement. Short-term plans, I think I've mentioned these, so exploring further the use of vision as a navigation sensor, for example, aiding the INS. Robust techniques, rather than the slightly bodged together systems we've got at the moment for repeatedly generating models from georeference data, and that's in its broadest sense, airborne, terrestrial, indoors, etc. Looking at whether we can actually do some of this SLAM type research for unreferenced data, and then looking at moving it real time as well, which is a requirement for certain folk, motion analysis, feature detection, modeling, etc. All good stuff. There's years of work behind each of these probably. Electronics, and again, this is just to show you some of the enabling things that we're playing with. If you've done electrical engineers in the room, they'll be probably slightly underwhelmed by this, but we're quite pleased with what we're doing. So just a simple little data logger that's time stamping within reason any serial digital or analog data solution. So you can see up the top right there, that blue and white square is an SD card, just to give you an idea of the size. So the whole thing's about this sort of size. Ignore the white development board on the left. And it's actually getting in there, messing around with the firmware, messing around with the hardware to actually enable us to do the time tagging task off an off-the-shelf sub-$100 data logger. And we can start stringing these together and actually get solutions that work in the real world. Real-time data transmission, again, one of our little model aircraft is designed specifically for operating as comms research aircraft, and there's some fun things we're going to be planning to do there. But getting data off real time, looking at 2.4 gig. So we've got these sensors, which are pretty reliable using some of the sped spectrum techniques that are available now, some of the directional antennas that you can see there. And again, it's working, it's out there, it's in the real world. We're also exploring some comms solutions up to 60 kilometers for a couple of potential clients at the moment. And again, we've got some skills around that area to be exploring what's going on. In-flight data collection board, and again, apologies for the fact that the top right, it looks a bit bodged together there, but it works, it's out there, it's flown over 100 flights. So it's recording raw GPS data at 5 hertz from 2 high sensitivity receivers, one on each of the wingtips, and then we can actually collect as much other data as we want from other sensors we might choose to put on board, other air data, for example, and store it for post-processing. And then bottom right, just trying to solve all of these issues that stop you doing stuff in the real world. So power supplies at a range of voltages that are robust, that are reliable. We've got lithium polymer battery packs, and actually then the means to break that down into, and I can't remember off the top of my head, is 3, 5, minus 12, 12, a range of voltages that the onboard sensors need on the UAV, for example. But you can see from the size of the AA battery there that it's not the largest thing in the world. Short-term plan on the electronics, then we're going to carry on looking at different sensors in its widest sense that we can use for RF positioning, and then looking at integrating those into our point software. One area of interest for us, based on some of the experience we've had to date, is actually a miniature low-cost data storage device that can grab data at, for example, up to 400 megabytes a second, and that has some potential applications, we think. And then looking at the longer range, ideally no cost, preferably public areas of the frequency spectrum for data transmission or flight control, etc. UAV systems, and again, I'm charging through this. I started this program a couple of years back in Nottingham with one vision in mind, which is safe, reliable, low-cost access to sky. I'm not an aeronautical engineer, I'm not a pilot, but I wanted to get sensors and systems up there. I could see great potential if we could do that in a reliable fashion. I don't personally think that UAVs, at least at the moment, are a replacement for people on the ground or aircraft or satellites, but there are a number of application areas where they could potentially provide some sort of cost-effective or actually innovative-enabling opportunity. Our areas of UAV interest, hopefully fairly consistent message now: nav guidance control, sensor integration, data image capture and analysis, presenting data to users. We've got some experience in VR, augmented reality, etc. And developing systems for use across a number of application areas. So although eventually a spin-out might drill down to one particular client or market or opportunity, the technologies behind them should ideally be fairly underpinning. So in the UK, we ended up with 6 small aircraft, none of which weighed more than 20 kilograms. Bottom right, a couple of $100, just a simple Tudor 40 model aircraft. And that had micropilot, autopilot, infrared horizon tracking, comms, twin GPS antennas, real-time video transmission at 2.4 gig, all within a payload the size of a large matchbox, weighing less than 200 grams. Top right, carbon fiber, Kevlar, 30 kilogram payload capacity up to 20,000 feet, 175, 180 kilometers an hour, potentially. We never pushed it that far, but that's at a place called Park Aberporth, which is a missile range out in West Wales, and they're used to folk doing silly things with technology. And so we could go and play that one there. On the left-hand side was just a large, if there's any modelers around, a double-sized senior telemaster, incredibly stable platform. It cost a lot. That was £700 to build. So I don't know what the exchange rate on that is, probably over $1,000. But that had a 10 kilogram payload and was just a great aircraft for trying things out. It just flew in up to 30 knots of wind. It just took off, it landed. The aircraft and the aeronautics were not the research area. And that's what we were after. These are some data products, so flying a digital SLR. So on the left-hand side, the ground resolution was about 20 or 30 millimeters. We've got thousands of these images, as you would imagine, once you start flying these things. Then putting it through like a photogrammetry suite, creating the author photos down on the bottom right there. Small area to start with, but actually getting it through the whole chain, which was the point. Here in New Zealand, the internal R&D for the first few months was actually do that point software. So the UAV program's only been going since March. So what you're seeing here is 2 months of effort, so no apologies for that. But we are getting on with it, and the guys are putting all their free available skills and expertise into this. We've got 3 small platforms. The research areas there, again, should be coming hopefully fairly consistent with what we are doing. And we're looking at the commercial potential even now, even this year. You can see our pilot, who's president of the Model Aircraft Association in New Zealand, flying at our West Melton test facility there. The three main aircraft we've got: Kaikoori Key, which is named after the New Zealand parakeet, 2.5 metre wingspan, 3 kilogram payload. That's actually a proper sized senior telemaster. So again, within reason, unlimited budget, unlimited payload, any idiot can pretty much do something. The fun stuff is actually getting it to work for a few $1,000s in a few kilograms or less. On the right-hand side, Korimako, there's an electric variant and there's a glow fuel variant, both flying quite successfully. Again, even smaller. And that's all that we want. We're just trying to see what we can do with minimal effort, if you like, and minimal cost. Those cost about $400 all in to build. This is our final UAV, Kakapo. Instead of a UAV, we've got an unvehicled aerial man. And I think I should trademark this because nobody else seems to have thought of this one yet. So that's one of my PhD students, James, who jumps out of planes and does daft stuff. That's Christchurch from about 7,000 feet, I think. My house just off by the coast over there, university just under his right elbow, which is where we're physically based. So yeah, watch out for that. Kakapo, by the way, is a flightless parrot, which breaks its wings falling out of trees reasonably regularly. So not wishing anything ill to... Yeah, absolutely, yeah. He's got GPS, he's got camera systems, you know, he's reusable. He's got hopefully. One of the key things, and again, this goes without saying, I hope, to do with the UAV operations, is actually prioritising safe operations. Everything that we do has to be done safely and in an operationally safe way. So we've got procedures in place, operational procedures in place for both new aircraft and getting those flying for operations in the field. We're working closely with the Civil Aviation Authority in New Zealand to develop a framework for mini UAVs in New Zealand, for example. We've already got frequency secured that's UAV specific in New Zealand. We've got inputs going into the World Radio Congress from New Zealand this year related to that activity. A number of other longer term actions, if you like, to try and secure a safe framework that is agreed by all. We've got dual redundant control systems on every single UAV, even the smallest ones. Segregation of the control systems and the payload entirely. And we've got 2 or 3 safe areas that we're playing in. So West Meltonisora, Hoka, Dalethorpe is the furthest away. That's about an hour away. And that's just down in the foothills of the Southern Alps. There are a few sheep around and idiots from the GRC sitting in their Land Rovers there pretending they're working hard. Yeah, no, it's pretty good at herding them. I've seen a commercial potential there. We're going to slowly whiz these things around and clear... No. So this is just a summary. So we're a couple of months in. So these are the systems and sensors that we've actually got up and running and integrated into the airframes. They're at a research level. Nothing's at a commercial stage where I could go and sell this en masse. But behind all of these, there's been a degree of research, a degree of activity, a degree of real-world actual research in getting these things out there and testing them to make them work. Ubiquitous imagery shots. So these are just the top left is the very first flight we ever did. Bottom right was one where we'd actually sorted out some of the vibration issues. So again, we're flying at about 100 meters, 20mm lens on the 400D Canon, getting about 20mm pixel size on the ground. And these we're flying repeatedly when we have control from the ground over when the camera triggers or not and focuses or not. And we can consistently get 3 frames a second for as long as we want till the memory card runs out. And we've got a large memory card in there. So stitching them together, good overlap, putting that through the photogrammetric processing tools. And again, you can see some of the field work. The yellow stuff is Trimble GPS kit. The white plates are A4 sheets bonded onto metal backs because this is actually a paddock with grass about this high that we're operating out of. And so that was doing some of the photogrammetric truthing and also just some of the scaling when we were zooming in. These are some of the sensing systems that I am demanding the team has in place by the end of the year, as is my right as head of the place, and I'm quite keen to move it forward. We've got down to the end of platform stabilization now. Texas Instruments is this week's job. Thermal imaging next week. The front end we should have within a month. We've got 3 autopilots we're exploring at the moment. 2 homegrown, 1 commercially available. And so we'll just keep on testing those, trialing those, comparing the operations of those, and work our way up to choosing hopefully one sort of variant as we move throughout the year. The operations, operationally longer term, we'll just keep on getting that experience. And there's no replacement, as you guys know, for getting out there, building these things, integrating the sensors, flying them, learning from the real world in your operations there. Continue to work with CAA to sort out the operational and legal issues. Potentially, and there's already folk demanding this, develop maybe larger, certainly longer duration aircraft. So on the right-hand side there, you can see a 4-meter wingspan aircraft we're speaking with an Australian company about developing. Kotaku is the white heron in New Zealand, and explore potential for early commercial operations even as early as the end of this year, where we can operate under model aircraft regulations if needs be and deliver something of value that someone will pay for. Short-term plans on this, get that photogrammetry process chain a bit more robust, speed up the time to actually generating the DTMs or those value-added products, look at the issues of long range, by which I mean 60 to 100 kilometre real-time video transmission of both thermal and infrared, visible and infrared data. The whole issue of autonomy, and that has safety issues, it has technology issues, looking at the operations there. Launch and recovery in difficult terrain. So we need to be able to launch without any runway. Hand launch, catapult launch, we need to be able to recover in the same if we're going to be actually doing some of the things that we think are possible. So there's some mech-eng issues to do there. Doing the initial analysis, probably on the commercial basis, of the cost-benefit analysis of the systems we are developing and seeing whether that stacks up for some of the early application and markets that we think we've identified. This is it, nearly there now. Just 2 more slides, and then we can get into the discussion. So future plans, aspirations, just 1 slide really. Choose a random date, 2010. We will be, and we have to be, world leading. I want people, as we are now, with firsts from Cambridge and elsewhere, knocking on my door saying, I want to come and do a PhD with you. I want to come and do research with you. And that's what's happening already. And folk are looking like this because of, they seem really excited, or they want to go and jump out of planes in New Zealand, or I don't know what it is, but they're coming along, and we've got to keep that going. Industrially focused expertise and skills, both in terms of the contract work we can do externally and the internal R&D that we're doing. Choose random numbers for size of staff and number of PhD students, etc. I mean, that's what's in the business plan, and that's what's in my mind, but it's got to be sustainable, and it might go one way or the other. A source of successful commercial spin-out, and within reason, as long as it's legal and vaguely ethical and a deal can be done that all parties are happy with, then it's there to be discussed, and I'm not going to try and prejudice what route or routes that may take. So just a final quick reminder, after all the flapping around and all the looking at all the details, final slide just to remind everyone, ignore everything else. That is our core business. That is the core skills that we actually have. The integration and underpinning knowledge of position orientation, imaging sensors and systems, getting them to do stuff in the real world that's of use to somebody externally. I thank you very much for listening.